Alright, welcome back. You have been missed. This is the second part of your video lecture. I'm going to boogie through these notes. Pause if you need them. Pause if you need it to be paused to fill in your fill-in-the-blank notes. We'll try to fit it in 15 minutes. Here we go. So we left off talking about the surface water currents, how those are driven by the wind patterns, and how it's a pretty circular and cyclic movement. But today we're going to talk about our deep water currents as well as some other sea floor features. But before we can talk about the deep water currents, you got to understand salinity. So salinity is the measure of the amount of dissolved salt in the water. Salinity equals how salty the water is. Generally, when we measure salinity, we don't measure it in like teaspoons or anything like that. We measure it in parts per thousand. PPT would be your abbreviation for that. The average ocean salinity is about 35 parts per thousand, which means for about every 1,000 grams or 1 kilogram of seawater, there's about 35 grams of salt. The average river salinity, in contrast, is about 0.5 parts per million, or if there was 1,000 grams of water, river water in your cup, about, let me do the math real quick, half of a gram of salt would be in your water, which is a very, very tiny amount. So the oceans, as you know, are much, much more salty than a river. Perhaps, though I don't advise it, you could drink a cup of river water. You would not be able to, or it would not be very good to drink river water or salt water at all. If you look over here, we've got a little chart of the ocean and how salty it is. Generally, you can see that we have little pockets of salt right here, which I think is really awesome to look at and kind of think about. So we've got a pocket of salt right here in the middle of our northern Pacific gyre, and we've got a pocket of salt right here in the middle of our southern Pacific gyre, which I think is pretty awesome and maybe something to think about. Right here we have got a huge concentration of salt in between Africa and Europe / a little bit of Asia. This is because, if you think about it, if you recall, or you will read in your reading later, that the ocean becomes salty because the rainwater falls on rocks over the sea. The rocks erode eventually, and some of the salt particles are picked up from the rocks, and they move downstream into the river, and then they collect. It looks like all of the rivers that drain into here have collected a ton of salt, and because it doesn't freely flow as easily with the rest of the ocean, it's not distributed. So the salt is stuck right there, which I think is something that is super interesting to look at and study. But that's for another day. Salinity and density, there's a distinct relationship. Again, I love talking about relationships in science, as the density of the water is affected by the salinity. We know that water with more salt is more dense. So really, really salty water is more dense. Water that's not really salty at all is less dense. The Great Salt Lake has a very high salinity of 28 parts per thousand. This makes it really easy to float because the water is more dense. Moving on though, so the relationship between salinity and density is that as my salinity increases, my density also increases, and as this next slide shows right here, more dense things sink. So if you look here at my egg, I've got regular tap water with no salt added. My egg right there will sink. On this glass right here on the right hand side, I have salt water. You can see it's even a little cloudy. There's a lot of salt in there, and that causes my egg to float, meaning that my tap water, my egg was more dense than my water, so it sunk. In my salt water, the egg is less dense than my water, so it floated. That shows the density change between water with no salt and water with a lot of salt. So salt water is indeed more dense. And Earth and Environmental Science will actually color some of this salt water, and you can see that we can stack the water on top of one another, and you'll actually see it sink or float. It's pretty cool. Just like there's a relationship between salinity and density, there's a relationship between temperature and density as well. This is an inverse relationship, meaning that as temperature increases, my density is decreasing, meaning that my cold water is more dense than my warm water. Warm water is less dense. Good. So as temperature increases, density decreases, meaning that warm water will float. This is key, both of these actually, the relationship between salinity and temperature and density is key to understanding our deep ocean currents. Convection currents in the ocean move warm water towards the surface and cold water deeper into the ocean. So while our surface water was more of a horizontal movement of water across the surface of the earth, our deep water is more of a vertical movement, and the water goes in a vertical direction, just like this. Fantastic. Well, it's actually opposite of that, but we'll talk about that in a second. When we talk about convection, this isn't something that just happens in the water. It also happens with our air currents as well, and it's the reason why we have wind. We'll talk about that in Earth and Environmental Science, though, another day. The key here is that as temperature, again, increases, density decreases, meaning that warm air rises. That's why a hot air balloon works. What you have here is our deep ocean currents, also known as the global conveyor belt. This should look familiar to you, this diagram right here. It's the circling of ocean water, and this, my friends, is driven by the differences in salinity and temperature of the waters. Low temperature water and high salinity is the densest ocean water. So wherever I have lots of salt in my water and really cold water, I know that I have very, very dense water, meaning that it's down low. These deep ocean currents flow under the surface of the ocean. Again, they're moving with more of a vertical movement. And these are important because they help move nutrients, oxygen, and heat with them. So while the surface currents moved primarily heat around, these ones move nutrients and oxygen as well. If we didn't have the deep water currents, we wouldn't have as an abundant of ocean life as we do have, because the organisms would use up all the nutrients in the system, and then we just wouldn't have any more. So these are really important, and again, they're driven by the salinity and temperature differences. The other ocean movement that we have is the tides. This is again due to the gravitational attraction of the moon, a little bit of the sun, but a lot of the moon. Because the moon is not big enough or large enough to have a huge gravitational pull, it doesn't pull the earth, but it does pull the waters of the earth. The gravitational pull of the moon will pull the ocean towards the moon. So you can see here this little light blue or teal area is what we call a tidal bulge. And the tidal bulge will move where the moon is. And just so you know, another bulge will occur on the opposite side of the earth. So this is pulling the water towards the moon right here, but it also does it on the other side too. Because of Earth's rotation, this happens twice a day, so we'll get 2 high tides and 2 low tides. Fantastic. So this is the inertia bulge due to the Earth's spin. Remember, inertia, for every action there's an equal and opposite reaction. This is the reaction of the gravitational attraction of the moon. You'll learn in Earth and Environmental that we do have a little bit of, the sun plays a little bit of a role in it, but not too much. Fantastic. Next, we will talk about our ocean, what's going on as far as where the earth meets the ocean, so underground. We have any land or crust that is underneath the ocean is called ocean crust. This is a thick layer of rock that separates the Earth's ocean from the hot mantle beneath it. There is still solid ground underneath the ocean. This is different from continental crust in a couple of ways. Continental crust is generally thicker than ocean crust. If you see, we've got ocean crust right here, ocean water over the crust, the continent right here. Ocean crust is generally thinner, it's generally more dense, It's generally younger than continental crust, and it has a different chemical composition than my continental crust. Moving on, in the ocean we have this phenomenon happening. It is called sea floor spreading. This is where our two plates in the middle of the ocean are moving apart. This is the divergent boundary. We'll talk about that when we go over tectonic plates in earth and environmental science. But basically the two plates are pulling apart right here, here, and here, and that allows for some magma to push out onto the surface of the ocean, forming some new igneous rock right there. And then it keeps happening, so the new igneous rock is formed right here, and then it keeps happening again because this keeps pulling apart. So it happens again and again. So we'll find really new igneous rock right here. This will be a little bit older still. Again, we'll talk about this in another lecture as well. This happens at mid-ocean ridges, so places where two plates meet. The youngest rocks, again, are found closest to the ridge right here. And subduction occurs at plate boundaries as well, but that is not pictured right here. Subduction is where one plate goes underneath another and becomes part of the mantle. Again, mantle is like a very turbid, liquidy magma right here. Very warm, melted earth. And then it comes up, cools, and forms part of the ocean plate. Some definitions to go through real quick. We have a couple of seafloor features. Continental shelf, this is the edge of the continent that lies under the ocean. Continental shelf right here. Continental slope is the break that descends towards the seafloor. You can see right here, break descending towards the seafloor. Continental rise is the final boundary between the continental crust and the oceanic crust right here. And then we eventually reach the ocean crust. The boundary of the continent is not the coastline, but rather the edge of the continental shelf. So this would be like our shallower ocean, shallower, and then it drops off, but we still got a little bit more. It's still not quite as deep until we finally get to that ocean crust. Other seafloor features. So we have submarine canyons, which are deep channels cut through the continental shelf. See right here, a deep canyon under the shelf. And then we have what we call an abyssal plain. Think of like abyss, like a deep, dark pit. Underwater plain usually lying between the continental rise and the mid-ocean ridge. This covers more than 50% of the Earth's surface. So this plain right here is mostly what the ocean looks like underwater, very flat. The last couple of things. We've got something called a trench, which is a long, narrow depression in the seafloor that forms when plates collide. Let's see if we can see the trench on this. Ocean trench right here, again, like a deep, dark pit. The Mariana Trench is the deepest part of the ocean, which is almost 7 miles deep. We have what we call seamounts, which are undersea mountains formed by volcanic activity, biological hotspots. So these allow for a lot of life right here. The volcano once happened, created some igneous rock, made a point right there, and often we find a lot of life right there. And then we have volcanic islands, which are seamounts that break the surface. So if this were the seamounts right here, if we were to reach the surface, then it's a volcano island like what we see in Hawaii. Mapping of the seafloor. So we map the seafloor using sonar. The sonar is used to identify ocean features. So basically it's a sound wave that are shot out down into the ocean, and then it bounces off the ocean floor and comes back. The time it takes for the sound wave to return back as an echo indicates the depth of the seafloor. So if it takes a really long time, then the seafloor is really, really deep. If it doesn't take as long of a time, that means it's not as deep. This equipment is mounted to the bottom of the boat, so somebody has a whole job like this. They sit out and they map the seafloor, and it's really cool. That's how we know what we know about the seafloor, because it's too deep, we can't go down and see it. All right.